Here I are on 12.7 trying to figure out these new coordinate systems. They're useful for different types of shapes, and it just helps us integrate things easier. Like, would I rather integrate x squared plus y squared equals 4? Or would I rather integrate something that just says r equals 2? One of these is significantly easier, and I know both of these are written improper, but it's the idea behind, hey, if I'm integrating something that's circular, I want to use cylindrical coordinates. Something in our standard x, y, z coordinate plane, it's called Cartesian, or it's called rectangular, because it makes great rectangles, but it makes terrible circles. Circles are overcomplicated, and even worse are something like a sphere, even more complicated. And so that's why these other coordinate systems exist to help us out here, but we're building off an extension of polar coordinates, so any moment on this circle can be described by r and theta. But we want to relate this back to Cartesian. We want to be back in our xy happy space. So how about this? Let's look at some triangles here. If I want to find the x value of this coordinate, I would use cosine. And that's where you see your favorite x is r cosine theta coming out of polar. And the same exact concept would happen if I had my y value as my goal, where this case sine OH would give me this. And so I'd end up with that great r sine theta is y. Other great things to remember about polar coordinates is that, well, x squared plus y squared, that's usually the type of equation we see for a circle. So how is this going to simplify and get nicer here? So let's see it. X squared plus y squared would be r squared cos squared theta plus r squared sine squared theta. Well, this just becomes r squared times cos squared plus sine squared, which I know makes 1. And then I'd be able to root both sides. So that's why this gets so much nicer. It's because that identity, cosine squared plus sine squared. And oh, don't forget, we're doing this in 3D, right? So don't forget that z is just equal to z. Z is untouched in this thing. We don't manipulate it. We don't change it. We don't care about it. Let's look at this angle. It seemed to throw us off in class that this angle opens past pi over 2. So if I'm looking at this angle, this is 0, this is pi over 2. This thing is going to open into quadrant 2. That's my measure of 3 pi over 4, and this length of the hypotenuse would be 2. So don't look at me crazy when I draw it out here, the fact that it's going to go somewhere back into this quadrant with this angle of 3 pi over 4. And then I'm going to drop this thing down 2. Again, it says convert to Cartesian. That means I'm starting here in cylindrical, and that's why I had my r, theta, and z. My r is this length here of 2. My z is this height here of -2, and this is my horizontal opening of 3 pi over 4. Let's keep on keeping on. And so we can see it, that this is 2, but I'm not going to really put 3 pi over 4 in here. I can. You know it's a horrible misrepresentation. That 3 pi over 4 is an obtuse angle. It wouldn't fit here, but the triangle always holds no matter how yucky the value is. So again, the cosine of 3 pi over 4 is x over 2, or 2 times cosine 3 pi over 4 is x. 2 times rad 2 over 2 is rad 2, which is x. And repeat the same thing for y. Sine of 3 pi over 4 is OH, y over 2. 2 times sine 3 pi over 4 is y. That's 2 times rad 2 over 2, which is rad 2 is y. I made a mistake. I already see it. Because this thing is in the negatives for x. So I just dropped that negative. This should be a negative rad 2. So when I come to my final coordinate, I have negative rad 2. I have positive rad 2. And for z, remember, z is equal to z on this front side. Negative 2. Done. This one wants me to convert from rectangular to cylindrical. Again, I'm in a weird quadrant with this guy. Like if I'm just thinking in terms of my normal coordinate plane, I'm over here -1, -3. So in terms of this guy, I'm in the negative x's and the negative y's. More on the y than x. So I'm somewhere out here. And then I need to lift it up 2 points. Again, I'm guaranteed that I'm starting with a triangle. We're just drawing triangles. That's all we're doing out here, where I have my x, my y, and my r. In this case, x is -1, y is negative rad 3, theta is unknown. But again, I can solve this thing out. Like Pythagorean theorem tells me that -1 squared plus negative rad 3 squared would give me r, which is just 2. That's just Pythag there, folks. And now I can use something easier than tan. Maybe my cosine is a little more recognizable, or my sine is a little more recognizable. Again, I'm in quadrant 3, so I have to be careful. X equals r cos theta. Again, I could probably do that a little bit smarter. That cosine of theta is x over r. That means my reference angle here is 60. But we know we're working in radians. So I know that's a pi over 3. And I just have to decide, if I'm in quadrant 3, how many pi over 3s is that? Well, it's passed from 0 to pi over 2 to pi to a little past pi. So I'm going to add 1/3 past a whole pi. And now I'm there. Again, my height is 2. So don't forget with me that z is z. And we put it all together. R is 2, theta is 4 pi over 3, and z is 2. Keep on keeping on for the sake of time, folks. Again, this is saying, please convert this to cylindrical. Please convert this to only say r, theta, and z, and nothing else. So I need to use those conversions. I need to use these little shortcuts that we've been developing and using to say, hey, if I see an x, it becomes an r cosine theta. If I see a y, it becomes r sine theta. And I do just that. This is, instead of 4x squared, I know that x is r cos theta. Anywhere I see a y squared, I should have r sine theta. And so I do just that. This becomes plus 4 r squared sine squared theta. And z, again, is unchanged. Keeping on with this, right, I can factor out the 4s. I can factor out the r squareds and use a little Pythagorean identity to simplify this guy down just a little bit more to its final resting place. Sine squared plus cosine squared is 1. So I just get 4r squared plus z squared is 1. And I might ask you something like, what is this the equation of? I think this one's a football. Because it's going to be a circle for x and y because they have the same stretch shrink, but it would be an ellipse on x, z. It would be an ellipse on y, z. So to me that says football. ellipse this way, ellipse that way, circle from the other direction. That's just my guess. Let's get spherical, and we got some Greek to accomplish. When I'm doing spherical out here, I think of it that the thing that makes spherical unique is this phi. And we'll get to it towards the end, but phi is really vital to think of how much this thing is opening. Let's start over here. Again, we're really used to this idea of r extending out here, and that theta controls how much it opens. Again, theta is opening this way. Theta is still the same as it ever was. Like, I could say that theta is still this x, y, r triangle. So you can get theta by tan inverse of yx. You could also get theta from referencing r cos theta, r sine theta. It's still the same ways we would have found this in the past. But now we get to rho, and where it says the radius of your sphere is no longer r. It's referred to as rho. So this just says, hey, I'm going to elevate this coordinate to help us out before we do anything else. Some amount of z. Well, let's make sure we label this bottom. Again, this is my hypotenuse. This is r, where my x and y are over here. I'm not going to draw them, the amount of y, the amount of x, because it's going to overcrowd my picture. Just understand that it hasn't disappeared. And that means rho has to be this. The distance from the observer to the point. I know it sounds a little obnoxious, but yeah, rho is just that distance to the point. I shouldn't have drawn it on that, so I'm going to write it on the other side. That's rho. And the convenient thing is, this is another right triangle. This is our new right triangle, where my base is r, my vertical is z, and my hypotenuse is rho. But you know that I need some kind of angle in here to help this relationship work out, and that angle is our friend phi. Phi comes from this angle. Phi says, hey, I'm looking down from the vertical to some moment. That is phi. Phi is if I look straight up at the sky and started looking down, 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 down until I found my object. That change between straight vertical and that object, straight vertical and that object, that difference in angle, that change in view is phi. Phi is not the angle of elevation from the viewer. That would be the other side. That would be the complement to phi, right? If the guy, how far he needs to look up. No, phi is how far he needs to look down. And so, because it's how far he needs to look down, it lands in a different place in my standard triangle. Theta is along the ground. Theta is horizontal. Phi is a vertical component. And so it hangs on the top, the vertical angle between the two. And now we have all sorts of things that we can do to relate these. Things like, yeah, I know that cosine of phi is AH, z over rho. I also know that sine of phi is things like r over rho, OH. But I also know that if r is x squared plus y squared, or, right, that phi is the distance formula. X squared plus y squared plus z squared. Right? Phi is just the distance to the point, so I would use the distance formula to get there. And again, there's other relationships that we can kind of generate, but ultimately, this kind of brings it all together. Let's finish talking about phi. Now, phi, it counts down like, pi over 6, pi over 4, pi over 3 to pi over 2. And phi could theoretically continue along here, but it stops at pi. Phi is locked in between 0 and pi. Why? Because if I wanted to look back this direction, I would just change my opening angle. Let's look at it open in this picture. If I wanted to look somewhere out here, I would just wrap my theta around, to like here before I decide how far I'm looking down from vertical. It doesn't make sense to look down underneath and around to this thing. I'd much rather keep my angle small and say how far I need to look from vertical and adjust my horizontal to get there. And again, more relationships that we can draw out here come from these. Let's get into some examples. I don't need to take that any further. And again, I don't know if you want to make note of this. It opens from the top. Might be worth writing very clearly there. On to our example. Convert this spherical to Cartesian. I'm labeling things. My spherical coordinate is labeled, phi, not phi, oh my gosh, rho, theta, phi, Greek. Okay. I'm going to start drawing triangles. That's all I can do is start drawing triangles, because I don't know if I can quite get there. It's hard enough, like if I sketch this thing, it's going to help us understand where all these values come from, but it's not going to help us find the x, y, z until we get to the triangles. So we'll get there in just a moment. This thing tells me to open up pi over 4. So about here, this is pi over 4. Then it says from the top, I need to open up down about pi over 3. That's a nice 60. And it says that long distance that I'm looking up, this pi over 3 opening, this distance I'm looking is 2. So the 2 is my rho, my z is unknown, my r is unknown, and that's where these triangles are going to come save us. Honestly, you might be interested in just labeling them blank before filling them in. Just good practice. I fill in the values I know. This is 2. This is pi over 3. This is pi over 4. And now I'm just going to work my way all the way around because I need to find z, I need to find x, I need to find y, I need to find r, I need to find all of it. And so I do just that. Z here is going to be my cosine value, because it's my adjacent. So the cosine of phi is AH, z over rho. So again, saving us a little bit of time. 2 times cosine pi over 3, that's 2 times 1/2, that's 1, is z. I'm done with z, put it in a box and basically never come back to it. Sine of this angle is going to be OH, r over rho, which again would be 2 times sine of pi over 3. And I know that 2 times sine of pi over 3 is 2 times rad 3 over 2, which would just be rad 3 is r. So if I finish labeling this thing, this would be 1, this would be rad 3. That means this would be rad 3. And the whole thing's coming home now, because x and y are going to be the same. So I just keep moving along, just keep moving along, just keep moving along. That means if cosine theta is x over r, or if x equals r cosine theta, that would be rad 3 times cosine pi over 4 is x. That'd be rad 3 times rad 2 over 2. That's rad 6 over 2 is x. And I would find a very similar thing with y. I know I'm running out of space a little bit. I'm trying to save room for my coordinate here at the end. But I know that y is r sine theta. And that would be rad 3 times sine of pi over 4. That would be rad 3 times rad 2 over 2, which would also be rad 6 over 2. And so I've got it. Rad 6 over 2 for x, rad 6 over 2 for y, and 1 for z. And guess what? This squared plus this squared plus this squared makes 2, makes rho. All right, folks, we're going to keep on to this last example where it wants me to convert equations. And again, all I can do when I convert equations is draw some freaking triangles. I'm just telling you. I'm just going to keep drawing these triangles until I'm blue in the face. R, Y, X, phi. That was a terrible right triangle. Z is always my vertical. R becomes my base, and rho becomes my hypotenuse. And so, if this thing is asking me to convert, this is my best place to convert. This is the place I always want to try to go, where, in this case, sine OH is y over r. Sine over here, OH, is r over rho. Well, it wants me to convert from spherical to Cartesian. So that means just moving my equation over a little bit. Rho equals y divided by rho, or in this case, rho squared is y. Well, like we said way at the beginning, rho is just distance. So if I came back to this thing, I could clean it up and say rho squared is x squared plus y squared plus z squared. That's the equation of a sphere that we learned at the beginning of the year. And so this becomes x squared plus y squared plus z squared is y. And I'd be so happy because it says convert it to Cartesian. Cartesian deals with x's, y's, and z's. Says, oh, why wouldn't you complete the square and make it pretty like you know it should be? The only thing is this is a y minus 1/2. It's not a nice one. So I get x squared plus this plus z squared equals 1/4. Again, this is a sphere. It's centered at 0, 1/2, 0 with a radius of 1/2. Here's some reminders, some nice recap at the bottom. Draw triangles. Draw triangles and use trig. Draw triangles and use trig. That's the best I can give you. And, you know, again, never forget that r squared is x squared plus y squared, like it says over here. That z remains the same. There are some other shortcutty things we can do, right? These feel really strong, but ultimately, it's just this that we did over here, right? Sine theta, sine phi, sine theta, sine phi, y, rho. It's all the same, and it all just comes from these triangles. Triangle!